Okay, welcome back everybody for the second part of the optimization and debugging and parallelization lecture. So again, we have Carl, and now we're gonna take a look at the optimization and parallelization in Python. So Carl, please go ahead.
Okay, thanks a lot. I hope, let's see, my screen works this time. So this is the next part of the lecture. So you've debugged your code, you've identified the slow parts, and you found that something needs to be improved. So what do you do? So do you see is my slide white now? It's changing?
Yes, it's changing.
Okay, so I don't have the problem I had last time. Great. So in this lecture, we're going to talk a bit about ways to speed up slow code or to optimize your code. And I'm going to cover basically 3 or 4 methods and then do some demos with those and show the subtleties of each one for basic optimization. And then in the second half, we'll talk about parallelisation, which is another form of optimization that adds a bit of complexity to what you're normally doing. So first, let's talk about optimization. So the first thing, I think you've seen this quote like 5 times in one of the previous lectures on last week, because I saw it a few times pop up. But you really didn't see the whole quote. So I saw that the quote that you saw before was premature optimization is the root of all evil. But in fact, it's the longer quote is we should forget about the small efficiencies. Say about 90% of the time, premature optimization is the root of all evil. So it doesn't mean you should never optimize or even prematurely optimize. It's just that most of the time you don't need to. The other thing is that if you look into who actually said this, it's not totally clear. So it's often attributed to Donald Knuth, who's the guy who created LaTeX and things like that. But it's also attributed to Suetonius Hoare. And both of them seem to blame the other for the quote. So no one takes responsibility for it. And the other thing is this comes from an article in 1974 on why go-to statements are good. So take it with a grain of salt. So it doesn't mean you should never optimize code. It doesn't mean you should never think about speed and optimization. And there's actually 2 reasons I'd say for that. And one, code that runs slow, let's say in the consumer world, like if you get an app on your phone, and when you click a button on it, it takes a few seconds for something to happen. It makes you mad, right? It doesn't provide a good user experience. And then in science, we have lots of big data analysis or simulation codes that we run. And if your code's slow, it delays the results of scientific that you could be publishing, and it ties up computing resources, especially if it's inefficient, that could be used elsewhere. So that means that if you're running on a big shared cluster, you could be taking up CPU time that could be used for some other interesting project just because you didn't optimize your code and it's running 100 times slower than it could have been by changing a few lines of code. So why would you optimize? I just gave you 2 reasons, but once your code is working, you do want it to be efficient. So you want to have a balance between, I'd say, usability and readability. So code that's not so convoluted that you can't understand what it's doing, and code that is correct. Code that's correct, and balance that with code that is fast and efficient in memory use. Now, of course, you can't always achieve both of these. So often, you should, I'd say, generally err on the side of usability and readability. But so especially if it's code that you have to maintain for a long period of time, because if you do crazy tricks to optimize your code that are hard to understand, it's likely that that they'll break in a future update of some dependency, or a new CPU comes out or something, and 2, that you'll forget how you did them or why you did them, and then you'll probably introduce bugs later on. So it's still better to on balance go towards clear, readable code than necessarily the fastest code. A few things that are important to mention is, one, that Python is an interpreted language. And though there is actually some compilation that happens, you probably don't know about all these PyC files that you see lying around your code after you've run it are compiled Python code, but it's compiled to an intermediate type of bytecode. So it's not compiled in the same way that a C code goes directly to computer bytecode. It's an intermediate bytecode that then gets interpreted again, but it's still faster than actually. So Python doesn't really execute each line. You know, it does some optimization, it does some compilation before, but it's still not terribly fast. And in particular, for loops are very, very slow in Python, just due to its interpreted nature, and can be up to 10 to 1,000 times slower than a for loop you would get in C. And so that's important to remember. There's a variety of ways you can speed up your code and get however close to the speed of C or low-level languages. And you'll see that in a moment. So it doesn't mean you should just say, oh, well, let's abandon Python for faster code. There was even, I think, an article I saw recently was circulating around. I think it's on Archive, so just a preprint of somebody who wrote this article saying that to save the environment, we should stop using Python in science. Or I'm paraphrasing a bit. I think I'm probably overly paraphrasing that a bit. But it was basically saying that writing in unoptimized code is actually generating you heat because of data centers. It's not totally true, though. So the example that they were using was, that Python, of course, is very slow, but of course, almost nobody in science writes their code in pure Python. You're actually using, and you'll see in a moment, even when you write in Python code, a large fraction of what you're using, especially to use libraries like Numpy, is actually implemented in C or Fortran very optimally. So the statement that Python is natively very slow is actually not quite true. It's because it's very good at running C code that's very fast. That brings another point, that it's not an inherent problem of the language. So we often, when we say Python, we're actually talking, we really imply that we mean C Python, the implementation of Python that you're using right now. So when you type Python at the command prompt, you're getting a version of Python called C Python, which is an implementation of the Python language. C Python does actually get generally faster each release. It's had a few regressions, but they do improve the speed of it each time. So that's nice. But there are other Python implementations that exist and that are trying to solve the general speed problem in a more general way. So there's one called PyPy, and I just put a link to it here. You can read that at your leisure, which is a fully JIT compiled Python. I'll tell you what JIT compiling means in a moment. Although I think you probably heard a bit about it before. It means just in time, by the way. So it's compiled when you run the code, not before. And there's also a project from, I think that was originally from Facebook, called Piston, which is a project to optimize C Python for certain use cases to make it much faster. And there's also other efforts to remove bottlenecks in C Python that are going on. So one of the things you can do to optimize your code is do nothing. Just sit back and wait till somebody smarter than you, implements a better version of Python, and then it just releases it, and your code just magically becomes faster. So that's actually the lowest level. That's level 0 optimization, is just sit back and wait for the people doing things to improve it to do it. Some notes on, I want to make a comment on this PyPy that I mentioned. So PyPy is, the idea of it is to take all of Python code and do just-in-time compiling with LLVM. And that might sound familiar to you, because I think we're going to talk about Numba in a bit, but I think Thomas Gall introduced this in one of his lectures earlier, that we have this thing called Numba, and you can JIT compile certain parts of your code. Why not? And I think somebody asked it even in the Slack, I think last week, why don't we just JIT compile everything in Python? Well, PyPy is an effort to do exactly that. It's not so simple, it turns out. It's a very complicated thing. It's a whole replacement for all of the Python language. It supports a large fraction now of NumPy, which is actually quite good, but not all of it. It also has support for C extensions. And this is the biggest problem, is that the way you write code, C code that works with Python, is very specifically C code that works with C Python. And once you go to something like PyPy, those extensions no longer connect properly. So it turns out right now in PyPy, any code that uses C code, like NumPy and others, actually run slower than they would in Python. So it doesn't necessarily give you the speed increase you'd expect, unless you're writing pure Python code and with no extensions. But it does support right now Python up to version 3.7. There's really rapid increases in this. And so this is just on the right here from their website, running some of the benchmarks compared to C Python. And you can see that there's quite a bit of increase for a lot of tests using PyPy. So the disadvantages of PyPy, though, is that, again, scientific code is often a mix of NumPy, SciPy, C, and even Fortran code, and it's often slower than in PyPy than it is in C Python. So it's not great, and it's because of these C extensions not being supported. But however, there are things you can do without having to switch your Python implementation that can make your code faster now without waiting for somebody to come up with a better version. But certainly keep an eye on PyPy, because I think that's a project to watch out. So the steps to optimizing your code are as follows. First of all, make sure it works. So there's no point in debugging or writing optimized code if the code doesn't work first, because during the optimization process, you almost certainly will introduce bugs, or if there is a bug there, you'll exacerbate that bug and you'll never be able to solve it once it's been optimized. So don't try to optimize code you're writing or debugging in general. What's the best thing to do is identify the use cases for the optimization. So first of all, how often is this particular function called? We could use a profiler for that. Is it even useful to optimize it? So I think in a lot of code, you might have a function that takes, like, let's say if a function takes 2 seconds to run, which is quite long, from if it's something, interactively being run, but it only runs once to load up some data or something like that. Then and the rest of your code takes an hour or 2 hours to run to compute its simulation and write it out or something. Then there's no point in gaining 2 seconds if the rest of the code takes an hour, right? So you could spend all day optimizing that 2 seconds, but it's not going to gain you much, right? So don't do it. So only look at functions that are called very often, or that are really taking up a significant fraction of the runtime. Then, of course, use a profiler, which is what we learned to do in the last section, to identify where those bottlenecks are in a more scientific way. So you can first just say, okay, this part seems slow, but no, see where really it is slow and why. And then try to rewrite, I'd say, as little as possible to achieve improvement. So you first try to see, is there a small thing you can do to make this improve without breaking everything and writing the code? However, if that fails, the step 5 is to really refactor the code, because sometimes it's really the design of your code that's the problem. So for instance, this was mentioned earlier, one of the Zen of Python is, flat is better than nested. That's actually true from an optimization standpoint, because modern CPUs can take flat data structures and parallelize them automatically on, using the features of their CPU. And that sometimes doesn't work if the data are nested or not local in memory. So, so sometimes it really means you have to change your data structures or change the way your code is written. So I'm going to give a few methods for speeding up code. And the first one is a really simple one, actually, and it's called memoization. And the basic principle of memoization is to don't recompute something, especially something that's slow, that you have already computed. Sorry, I'm just going to turn off Slack for a moment because it's making noises in the background. Let's close it. Okay, so yeah, the idea is that if you have something that takes a while to compute, but you compute it more than once, cache the result. That's the idea. So basically trade memory for speed. So and people basically come to this. This really is a computer science term. You can look up whole papers on how to do memoization properly. But people tend to come up with it on their own because it's a kind of a design pattern that it seems kind of obvious, and you probably have done something like this before. And I see a lot of code like this written by people who start writing code and for scientific purposes and haven't really heard about memoization. So they make a little cache dictionary. So here, and let's say they have some function called a do large computation here, and they wrap that function in another function here or in a loop somewhere, and they say, if the result is in the cache, return that result. Otherwise, do the computation, and then set the result into the cache. And this really works. This will speed up the code that you're running, but it's not very Pythonic, and it looks kind of ugly, like to have this everywhere, especially if you do it very often. And also, if there's many values of x that you're passing into your do large computation, memory is just going to increase here and never get released. It'll just blow up. So of course, as usual, there's a better way to do this. And one of the things that I've learned, often the hard way, after implementing something in Python, is that there's always something in the standard library that does what you were thinking about for you. So always look and read through the standard library notes or the standard library reference when you're bored one day, and just look through the things and see if you can understand where to use various tools. And one of the really nice packages, Func Tools, that's part of the standard library of Python. So you don't have to download anything, it's just there. And one of the things it includes is something called LRU Cache. The problem is the name is a bit cryptic. But this does memoization as a decorator, and using a particular method called least recently used. And that just is a way of caching that it throws away items that, if you run out of memory, it throws away items that are not accessed recently. And to give this, you have to just specify roughly the expected maximum size that you need to cache, the number of different items you'll probably be passing in, just roughly. It doesn't have to be perfect. And it uses basically a hash of all the inputs to the function that you give it as a key to basically a results cache. In the implementation isn't exactly like this. It's a bit more complicated, but the effect is the same. So all you have to do is take your large computation function, and by the way, it can have multiple options. It can be X, Y, Z. It doesn't matter, and just put this decorator on top of it and give it a max size, and that's it. So that's done exactly what this code has done, but in a more clever way, of course, written by somebody who's thought about the problem more, and requires just one line to add to your function. So it's really nice, and it works in many situations. And again, I'll do a demo of this just like in the last one after a couple of slides, but I'll first set up the list of things that you can do. So the second way you can speed up code is simply use Numpy. So for loops in Python are very, very slow. As I said, they take a time, a measurable amount of time to execute each iteration of loop just without actually doing computations. Just doing the loop takes effort. Numpy tends to favor what we call vector operations, meaning that you define an array and or a vector, sometimes it's called in C, but an array, and you operate on that array all at once. So you make, instead of doing a for loop like this, where you say for I in range 100, X is I times 0.1, and then I is f of X, you just make an array of all the possible inputs and then operate call F on that array. And so this is a vector method of doing the same thing that you would in a loop like this. And the important thing to remember, and I think this is probably covered a bit in the NumPy and SciPy lectures, but NumPy is implemented in C and Fortran even. And not only that, but it uses behind it some very, very fast numerical libraries that are optimized for your CPU. And I'm going to talk about these a bit more in detail later on in the parallelization session. But two of those are the Intel Math Kernel Library, MKL, which is a closed source piece of software from Intel, but that's included actually with Anaconda, and it's compiled into NumPy if you install NumPy from Anaconda. But also there's two low-level libraries, BLAS and LAPACK, that are used by a lot of the NumPy functions. And these are standard libraries that have actually been around for, or let's say maybe not standard libraries, but standard APIs that have been around for 20 or 30 years, more than that actually. I think they're from the 1970s, even some of the, I think, BLAS. And there are implementations of these that are extremely optimized for your CPU. So these basically do linear algebra functions. And if you look into the NumPy code, NumPy just calls one of these functions, and whichever version of BLAS or LAPACK you have installed will get used. And those are so heavily optimized that there's no point in so if you think, oh, maybe I'll write a faster linear algebra library, a faster dot product, it's basically a futile thing to do, because these things have been around and being optimized for 30 years, 40 years. You're not going to do better probably. So just use NumPy. And NumPy, you get the benefit of people who wrote very, very fast code, and these keep getting better, and they keep getting applied to better to each new processor that comes out to have better optimization. So like I said, the version of BLAS that's used right now in NumPy, I think if you install with Anaconda, is this MKL version. I think I have to check that. You may have to now install MKL as a second package. I'm not sure, but you can get it to use this. And then if you have an Intel processor, then you get a huge speed boost. So anyway, just vectorizing your code, avoiding for loops, gives you a lot of performance. Now, that's something that's not quite easy to do. I think, especially if you come from C programming, it's a very strange way of operating. I think if you started out writing code in like MATLAB or IDL or R, then you probably are much more used to this method of programming. But if you come from C and you're used to writing for loops, I always notice the first Python code that people write looks like this because they're used to C. It's the wrong way to do it. It takes a bit of thought. And the other thing that I found also the hard way a lot of times is that the NumPy and SciPy always have a function to do what you need. So if you're doing some crazy way of trying to index some bit of an array in some crazy way, there's probably a function already for that. They've really thought about everything. So just read the API documentation, and it just takes practice. So just keep practicing, or look on Stack Overflow, or ask people to see how to help to take a program that has for loops and how to remove those for loops. However, if you can't remove the for loops, there is another fallback, or even if you can, and that's Numba. And I think this was mentioned already in the first sessions on earlier in the month, or earlier in the week. And this is basically a way that you can take a piece of Python code using it just put a decorator on the code. So you put @JIT. And it uses introspection to look at the abstract syntax tree of this piece of code, and it turns that into code that can be compiled by an external compiler, LLVM, and makes a very, very fast version of that code that then can be called from Python. It can also be used to generate NumPy ufuncs. I think you covered. I think those were discussed in the NumPy section. So those are very hard to write normally. You have to know a lot of tricks, and it's very complex to write C code that does a ufunc. You can write them basically by adding a decorator. And you can even do really advanced things like compile a function to GPU code. That takes a bit of extra effort for NVIDIA CUDA and also now AMD ROC GPUs. Numba operates in 2 modes, since this is one of the caveats. No Python mode, which is the mode that you want, basically. It basically compiles the code to something that doesn't use anything from the Python library at all. Just returns a result. So basically compiles into like a C. You go into the function, it runs everything in a compiled, just like you would in a C piece of C code, returns from that function, and then goes back to Python again. But that means that you can only pass in values that it understands that are not Python types, with some caveats, because it can translate some of those types into code, such as NumPy arrays are actually okay. And it only supports a subset of NumPy and SciPy operations. So there might be functionality missing that you have to implement yourself. Object mode will actually take any Python function or any Python object and will work, but actually it gives very little speed increase in most situations. You basically never want to run an object mode if you can avoid it. So to force no Python mode, you either set no Python equals true when you call the JIT operator, or just use this njit operator, which is they provide. And the nice thing is the njit will just fail. If you call a function with njit and the code cannot be compiled, it'll fail, and it'll tell you why. And then you can say, okay, I need to implement this bit because it doesn't understand this part, or it doesn't understand this input. And then, so it's a bit annoying because things fail quickly. It's not as automatic, but you have to, then you know what to do, and you can rewrite the function in such a way that it can be sped up. There's even discussion that will become the standard in the future. The other thing about Numba is that you have to remember that when you have a hierarchy of functions, like a call stack, like we showed before, you have to JIT everything that's every function that's called by every other function. So this is an example from their documentation. So there's a function called create fractal, but that create fractal function calls mandel. If mandel isn't also JITted, this whole thing will fail, and it'll run in object mode, and you'll get very, very slow results. But once you also JIT mandel, then this becomes super fast. So you always have to, so there's a lot of thought you have to put into when doing Numba optimizations. The other thing is that Numba does work with NumPy. So even if you've vectorized your code, Numba can actually help sometimes. It supports a fraction of the code from NumPy. And if you look at this link here, I'll just open it up. You can see that a list of all the Numba functions that are supported by NumPy, or sorry, NumPy functions that are supported by Numba, rather. So things like cumulative sum, conjugate cumulative product, flatten, ravel, most linear algebra operations, not all of them though. And you'll notice a lot of these have caveats. They'll say like only non-string values in P, or only the first 2 arguments of this function. So sometimes there's arguments that are just not supported. So it isn't a full implementation of NumPy, but you can do most NumPy functions. So why would you even run Numba on a code that's already written with NumPy? Isn't it already fast? Well, there's a few things that NumPy can't do, and that's the main thing, is to minimize intermediate results. So if you have a piece of code like this, where you say x equals some range, and then you say result equals a times x squared plus b times x plus c, it actually first computes x squared. It also computes b times x, and then it computes a times x squared, and then it computes a times, or let's say this times this, and then it computes the whole expression. So in between, it's used some memory to store these extra intermediate variables. In memory allocation is slow. Actually, that's something that it takes a bit of overhead. So in C, you might do it like this. You would just make a for loop and say, all in one loop. You wouldn't use any extra memory. You would just fill the results in one loop. Well, what Numpy can do is take a NumPy expression like this and automatically turn this into one loop rather than 1, 2, 3, 4 loops or whatever. That's actually internally inside NumPy. So you do get a speed increase. The other thing is I mentioned that you can do things like there's other tricks you can do to make Numpy work better. Like in some cases you have to specify the input and output types rather than having it automatically infer them. So then it's not quite as automatic as what JIT, but you can get some better speed with that. You can generate these U functions, I already said, with vectorize and GU vectorize. And this basically lets you write code that operates in a one-dimensional array and have it automatically broadcast to n-dimensional arrays. So that's sometimes hard to think about, if I have a 5-dimensional array, how do I index the things properly to do this? Well, you can write it as a one-dimensional array, then have GU vectorize broadcast it properly to an n-dimensional array. So there's things like that. So I'm not going to go into details of these. I'll show some demos, but not quite at this level. But this is something just to remember that it can do. You can also do parallelization automatically, and we're going to talk about that in the next lecture. So the summary of this optimization, this is really quick, and I'm going to now go do demos because we have, let's see, how much time are we on right now? Let's check that clock. So it's almost 11:30, so yeah, good, we have plenty of time. So identify bottlenecks and then use NumPy and Numpy. Sorry, this is I should have crossed out Cython. This is from an old slide. I'm going to talk about Cython actually in the demo, but it's another method of optimizing code. But I would suggest starting with Numpy and Numpy first, only because now those are quite mature. When I first gave a talk about this a few years ago, Numpy was not very mature and it was hard to install. But now that that's there, I think it's much the simplest choice. But I'll show you Cython as well because it's also interesting. To improve the bottleneck and basically try not to obfuscate your code too much to achieve speed. The readability still does count. So let's look at some demos of this. This is where it starts to get interesting. So let me go to my Jupyter lab and let me close that. I'm not going to open that, and let's open up the optimization notebook. So I'm just going to set up some, and so I just like what I did in the previous optimization one, I made this little plot performance function to help me plot, the results from TimeIt, because we have to profile it first to be able to know what to optimize. And the first thing I'm going to talk about is the same piece of code that we had before for the Fibonacci sequence. This is the fixed version, so it works now. But one problem, if you run let's say just this compute golden ratio function, and I give it, let's say, start it with a 10th Fibonacci number, I get a result pretty quickly. If I go to 20, okay, it's still pretty good. Let's go to the accuracy of 30. Now it's taking, notice it took a second to go there, 40. Now it's taking a while for my computer to compute it. And so what I can actually do is this is just to illustrate this, I called the TimeIt function on this for the first 30 numbers. Actually, the 41 is taking too long. I'm actually going to stop it because I don't want to wait for it. So let's run TimeIt on the first 30 integers, and you'll see this is the time it takes to compute basically the ratio of the first 1, 2, 3, 4, 5 pairs of Fibonacci numbers. And this looks bad, right? I mean, it's going up exponentially. So we basically have an algorithm that's ordered k to the n, which is not something we want. So can we fix that? Well, one of the things we might think of is when you look at the Fibonacci sequence, we're calling itself recursively very often. And if I called k minus 1 or k minus 2, it's actually going to be the same result. So k minus 2 will be the same result of k minus 1 on the next iteration. So in fact, we're recomputing this many, many times. So it's probably not optimal. So what we can do is put at the top of the function from functools, LRU Cache. And then all we have to do is put at LRU Cache, and let's say max size equals 1,000. I don't know actually how many I want to put here, but that should be fine. Now let's make that same performance plot. Now first remember it looked like before, exponential going up to a few, almost 0.1 seconds after about 30. Let's run it again. Now, interesting, right? It's now jumping around crazily, but it's all 10 to the minus 6. It's incredibly fast. So now if I run, I should have pasted that function. It's got compute golden ratio of, remember 40, I had to stop it because I couldn't compute it fast enough. It's almost instantaneous. If I do 100 now, it's almost instantaneous. If I do 1,000, it's almost instantaneous. So really, this made an enormous speed increase to the code just by caching a result so it doesn't recompute the same result many times. And that's because this algorithm is a tree. It's computing for every number. It was calling itself many times, and the number of calls went up exponentially. But now they don't go up exponentially, and you get basically linear time. So it doesn't cost much to call this. There's some variations here just because of the caching mechanism. Okay, so that's a simple example, and that was memoization. But now let's talk about using numba and numpy and things like that. So to do that, I wanted to do something a bit more exciting. So this is a real world problem. So I wanted to solve a differential equation. And this is the heat equation. So du dt equals alpha times gradient squared of u. This is an equation that you know from thermodynamics. And the way to solve that in a computer is basically to discretize the partial derivatives. It's like this. So this is that's a whole other lecture, but you basically break it up into small steps. So you say the next time step divided by some finite step in time, and you can just subtract the next iteration from the previous iteration, is equal to an expression like this. So this is basically some. Let me just take a step back here. What we're doing is taking u, which is the heat at the time, at time step k, and we're putting it on a grid, and we're a discretized grid. So we have a grid of positions, and for each time step, we loop over the whole grid and compute the next version of how the differential equation will evolve. So this is a really simple example. It looks maybe more complicated, but it's very easy to derive this yourself. So first we say, okay, how would we? So what we want to do is just solve for u ij of k plus 1. So we can move these on the other side and write this as a function. So first of all, let's make an initial conditions for this. So I want to define my initial grid u. So here I just created a little room here, and the room has 2 space heaters, one on the left and one on the right. And somebody brought a hot brick into the center of the room and just set it down in the center of the room. That brick will cool off over time, and these space heaters will heat the room up. So that's how the heat equation works. That's what we want to do. And here's our solution. This is the naive solution. So I just said, I'll just do it with for loops. There's no numpy, nothing in here. So I have my initial conditions. I create some temporary arrays to store the previous and the current result. And I then loop over all the points in this grid. So it's a 2-dimensional problem. And then, for these are the points in the grid, it's a 2-dimensional problem. And for each iteration, I compute the next time step, and then I want to see what happens after n timestamps. So that's good. And I'm also going to define a little equation just to plot the results. So this will plot the results after 2 time steps, 10 time steps, 100, 1,000. And so let's just run it. So this takes, on my fairly fast machine, this is taking some time. Hopefully not too much time. When I tested this, Zoom was not running in the background. Okay, there we go. So you can see that it started out, the heat is diffusing away from the hot brick. And eventually it cools down completely, but the space heaters here can continue to heat the room. And you could run this for more iterations. If you wanted to find appropriate stopping time, if you were doing this properly, there's a bit more you would do to this. So the question is, can we write an improved version of this? Obviously that took a while to get to compute this. So how did we do it? So I left a blank here for you to try your own, because I think my solutions are reasonably good, but there's probably a smarter person that can do something better. So you can put your own in and try it. But here's my results for doing it. So I first of all, I reduced the number of iterations. I'm not going to do 1,000 iterations every time because I want to use time it, and it would have to run 1,000 iterations, many times. So I'm going to start with a smaller problem, 50 iterations, and just run that same code that I had above. And I'm doing the same trick where I keep the results in a dictionary here. So 661 milliseconds to do 50 iterations. Now, what about numba? So to do numba, I don't have to do anything. I can just take my equation, solve heat equation loops, and call ngit on it. By the way, this is the same thing as putting the ngit as a decorator on top. You can just call a function or use the decorator as a function. It'll return a new function that's equivalent to putting the decorator on the function. So here, that's all I had to do. I just turn that into numba. I run time it on that, and I get a result that's already, you can see, much faster, by an enormous factor, almost 2 orders of magnitude. So here's my plot now. And what I'm going to do here, I'm going to right click on this. I don't know if this is a trick you might not know. So in Jupyter Lab, at least, you can't do this in Jupyter Notebook, but in Jupyter Lab, you can say create a new view for the output. And I'm going to put that over here. It'll be down here. Now I'll put it there. And I'm also going to take this this notebook itself and make a new view for it. And I'm going to put that below it. Maybe I'll put it above it, actually, because you probably have me blocking you right there, right? So the important thing is to see this output view, and then I wanted this to be at the cell where I can execute the cell. Where was it? So it's golden ratio. Here we are. So now I can rerun this cell when I need to. Okay, and then it will update. So it'll update this. Okay, so next let's start with NumPy. And so with NumPy, I have to make this a bit smaller because this code is a bit larger. The way I solved it with NumPy was basically to get rid of the 2 inner loops. So I still loop over iterations. And this is why I said you probably could maybe come up with a better way to do this. And instead of doing the inner loops, I just make them into NumPy operations. And so I defined some NumPy slices for 0, +1, and -1. And then I basically index them with these slices. So that's one way to do it. You could also make a derivative matrix or something like that. There's a few different implementations you could do, but this basically looks very similar to the code. So I see previous of 0, 0 is equal to alpha delta t or delta x times previous 0 -1 plus previous -1 0 plus previous 0 0 previous 0 +1 +1 0. So it's the same code, but done all without those 2 inner loops. So very simple. Let's just plot it and we see we get the same result. Notice it went quite fast, right? So the result looks good. If I do time it on that. So this is just getting rid of those inner loops pretty fast, right? And if I re-execute my, I lost my, here it is, my Excel. So re-execute that cell. Now you see we have loop, numba, NumPy. NumPy is actually not bad. This is, by the way, this is on a log scale here. So these are really close to each other. So if I plotted that not on log, let's get rid of the log for a second. Basically loop takes a long time. Numba and NumPy are pretty similar to each other, right? So I only put it on log just to see the really subtle differences between the results. So just writing a NumPy, you don't need any numba, you don't need anything fancy. Just writing a NumPy made a big difference. What about the 2, NumPy plus numba? So here I take that same equation, I ngit it. And by the way, it's something I didn't mention before. It's good to first run the function, which I did above, before you do time it, because numba, of course, the first time it runs, it has to do a compilation step, so it can screw up the statistics. It'll increase the error bar. Now I run NumPy numba, and let's plot that one. Okay, so now you look, it's between the 2, actually. Interesting. So it's faster than NumPy, but it's actually not as fast as the loop version of numba. So that's interesting. It's not, so it doesn't necessarily give you, it's not always clear which is the best speed. Then there's something called Cython, which is something I didn't talk about in the lecture notes, but I think it's interesting to mention. And it's something because it's a bit older technology. It's a Python-like language that basically translates, or it's basically allows you to write code that's almost exactly Python, but not exactly. So it's not, unlike Numpy, it's not really Python code. There's some extra keywords like cdef you see here, you notice C import. And these basically let you define, like in C, the data type of different objects. So here I define the data type of my previous incur array. And I also define the data type of all the inputs. So I put like int iterations, just like you would in C, double alpha, double X, things like that. So you have to do that. And what Cython does, it takes this code, turns it into C code, compiles the C code, and then links the C code as a as a Python extension. In a notebook, it's really easy. You can load extension Cython. If Cython, you might have to install Cython. I can't remember if I installed it or not in the environment, but and then run the code in Cython, and it will compile the code. And then if I run again, time it. So this is not just in time compiling. This is really compiling first. Then it runs always. So it's not like Numpy in that you really do need to compile it. If you write a lot of code that's Cython in your real analysis code, let's say, you have to include it in your setup.py, and then you have to always run setup.py build every time to recompile it whenever you make a change. So it does add some complexity to writing code. But the results, okay, look at the results here. Cython is actually pretty good. It's about the same as Numpy. In fact, in some of the cases when I tried this earlier, it was actually better. And it depends on the optimization flags. You can give flags like -03 to the C compiler. Is that right? I have to remember what the actual option is. Well, I can go to -- compiler because it's really easiest. I don't know what the defaults are. 03 might be the default, so it could be that this will make no difference, but let's just see. Yeah, it looks like the default probably is 03. So the difference, yeah, it didn't change it. But one of the interesting things you can do is also, if you want to see what it's actually doing, you can run it with the -a option. And it'll compile it and show you what it compiled. So at each line of code, it turned this line of code, delta t equals delta x squared over 4 alpha, into this C code. So it's a little bit ugly C code, but this is C code. So some of them get very complicated. These are all, so it creates a very complex C program that you would never want to write yourself. So here's the actual step of updating the buffers. And it looks absolutely atrocious, but actually the speed is pretty good when it gets. So you can actually see what C code it writes if you want. So that's the annotate function of it. Get rid of that, so it's a bit ugly. Great. So in the end, what we see here is one. Okay, this is basically illustrating what the problem was. Is don't run with loops, because loops are very, very slow. 2 orders of magnitude slower, in fact. Just running NumPy probably is all enough. If you just use NumPy, you're going to be in the ballpark of the best speed. You can sometimes get a bit more speed with NumPy. And by the way, this is something I'm going to come back to this in the next lecture, because there's another trick you can do here to get this even faster. But we'll come back to it. Cython is actually pretty good, but requires a bit of extra effort, because it is not using the same code. You have to add a little bit of information to the code. And I actually had to play with this a few times to get it to work properly. So I found that this made the biggest result. So defining that this was an ND array as a double with 2 dimensions made a huge speed increase. If I got rid of that line and let it infer that, it got very slow speed. So it takes a little bit of practice in playing with it to get it to work. How are we on time? This is the end, I think. So anyway, we'll come back to that in the next lecture. So that's my example. So I guess, why don't we break for a couple questions, and then we'll go on to the next lecture in maybe 2 or 3 minutes, if there are questions.
Thanks a lot, Carl, for this introduction to optimization. So we've watched this lecture. I think there might be 1 or 2 questions to address. Check. So there was one interesting question, just going back to NumPy. So the question was, if NumPy is already written in C or Fortran, why does it not directly perform the whole operation as one single loop, but needs to allocate intermediate results?
Yeah, because unfortunately, it doesn't know that your operation is one single. It doesn't know that you're trying to do 5 computations at once. It only, the Python interpreter calls each part of it separately. And then once it gets called, it goes into the NumPy C code, runs it, but then it comes back to the interpreter. The interpreter says, okay, now there's the next term I want to combine. So each time it has to go back to the interpreter, do something, and then go into the C code. So there's no way for the C code to know that you want to do multiple things at once. However, there's a caveat to that. There are a couple of ways in NumPy to get around that, to tell it that you really want to do a few operations at once. One of them is called num expression, I think, right? Num expr, and I think Thomas Gal mentioned that briefly in his talk. I don't know how well it's supported, but that's one way you can basically give it a string version of the NumPy expression. It'll kind of do a little compilation step, because that requires a compilation, right? And see, if you want to turn 3 for loops into 1 for loop, you need to recompile the code, right? So it has to recompile to do that. And the other thing is the einsum, NumPy.einsum module, which does also a little bit of, it lets you do kind of, what's it called? Tensor arithmetic in using the Einstein summation convention. That's why it's called einsum. So if you're writing code that does, I don't know, computational general relativity, where you have lots of tensors that you're multiplying in Christoffel symbols and crazy things that you want to, loop over, it can be used for that. So it allows you you can write down the expression of what bits it needs to combine, then do it, and it actually does it in a more efficient way than it would be if you called them separately. So there's ways around that, yeah. But generally, yeah, it doesn't know what you want to do. It would need to do some sort of compilation or analysis step to optimize that.
Okay, thanks a lot. There was a second question just on the max size parameter of the LRU cache. So what does it actually mean?
Oh yeah, so it just tells you how many results you want to store, a maximum amount of results you want to store. So it just limits how much memory gets used. So that's why I say you should try to kind of guess how many different types of values you pass to the function, and make it larger than that. And that will give you the best performance. If you make it smaller than that, let's say you're going to end up with 1,000 values, but you only make the size 100, you won't get as good performance, because what it'll do is it'll get to 100 and then it'll throw away some of those results, and then it'll have to recompute them. So it recomputes when it doesn't have them in the cache anymore. So it only computes, it keeps 1,000 or whatever you set it to elements in the cache, and then if they're not there, it has to recompute them. So it's again a trade-off of memory versus speed.
Okay, there's just one last new question. The question was, is there something like a cache in C++ as well? Or should we just simply write it on our own inside our code?
That's a good question. I haven't, to be honest, like I said, I haven't been doing much C++ code in a while now. The last I think I used was C++ 11. But C++ 11 already introduced a lot of really nice things in the standard library, and I think C++ 18 or whatever the latest one, and now we're at 20 something. The standard libraries have grown a lot, so I would first check the standard library and see if there's something like that. There might already be. I mean, caching is a very common thing to do. If not, there's definitely people have written libraries for this, right? I mean, but without using an external library. I don't know. I'd have to check. Yeah, I'm not sure the answer. Maybe someone can answer on Slack if there's a standard library for caching in C. Okay, thanks a lot. I think that's it so far. Then I guess we just continue with the second part of the. Okay, great. Yeah, this is. Let me see here. So where's my lecture? Okay. So parallelisation. This one I think is going to be a bit shorter anyway. We'll end a bit earlier, I think, because I actually didn't know I had to give this lecture, and so I made it kind of last minute. So so this is now we're moving on to another way of speeding up large computations. And basically the idea is that it can be beneficial to run non-sequential parts of a computing task, of a particular analysis task simultaneously. So maximizing resources use if you have access to either two things. One, a single machine that has multiple cores, which most of you do know. I think it's basically impossible to get a non-multi-core machine these days. Or if you have multiple machines in a cluster, then there's ways that you can speed up code that way. Both of these have introduce one complexity, and they also some pitfalls in how you develop them, but can give some very, very big benefits. So the first thing I'll talk about is how to do some parallelism on a single machine, because that's what you have available on your laptop. And first I'll talk about multi-threading and multiprocessing. And I'll talk a bit about vectorization, but we kind of discussed that already, so I think maybe I'll skip that. So that's just the concept that modern CPUs can actually execute more than one instruction at once in a single core. So a single core can execute, let's say, 5 instructions. I say modern CPUs, but actually, when I was in, doing my undergrad degree, we were working on, I think, VAX machines for one of the classes I was in. Running Fortran 77 code on VAX machines, and VAX machines, which are very, very old, systems, had vector processing, built into their CPUs back in. That makes me sound older than I am, that we were using very old machines at the time, but VAXs were used, I think, more in like the 70s and 80s. So they were already old by the time I was looking at them, but they already did vectorization. So meaning that you can execute multiple instructions. And so in modern CPUs, it's called usually AVX or SIMD. There's different names for this, but that's the idea, that you can execute multiple instructions. So I'll talk briefly about that, but not really in detail. Okay. So the first thing I want to talk about is multiple processes and multiple threading, multi-threading, which is one of the big differences with the various implementations of Python. And so you probably know that on your computer, everything that you run, every application you have open is running in something called a process. And sometimes processes can have child processes, so they can actually be, so things like if you start up Google Chrome, for instance, runs each one of its tabs in a separate process. But you can run many, many processes on modern computers. So if you're running on DOS from the 80s, it can only run one process at a time. But in modern computers, your operating system does multitasking. In fact, it does preemptive multitasking, meaning that it handles managing the running of all processes. In the processes themselves have no say over when they get executed. So each process has an ID. So if you open up your terminal and type top, it'll bring up a list of all the running processes in order of how much CPU they're currently using. And you have to type Q to get out of that. Or if you open up, and if you're in Windows, hit Control Shift Escape, I think opens up the task manager. Or Mac OS, you can open up I forget the name of it, the process viewer for Mac OS. And you see the same thing, a table of all the running processes, what they're doing with your CPU, how much time they're using, how much memory they're using, things like that. In a process, though, the processes themselves kind of run in independent memory segments, so they don't share any data. So one process can't access the variables for another process. There's a slight caveat to that there is ways via what's called POSIX shared memory to actually do that, but in general, that's not used, and you won't ever use that probably. So in order to exchange values between one process and another, they have to send or receive messages somehow. So either using a socket or a queue of some kind. There's lots of different methods for sending messages back and forth, or a pipe. There's another abstraction of how code runs, and that's called a thread, and that's kind of like I would call a lightweight sub process. So it's like starting up a process that's underneath the process that you're owned by the process you're running, but it has extremely little overhead to start and stop. You can start hundreds of them or thousands of them in a fraction of a second, and it doesn't take any extra memory overhead like you would with a process starting up. And memory is shared with a parent. That means, yeah, great, I can create a data array, and then all the threads can see that same data array because they're all running on the same machine and the same memory. But of course, that introduces some problems that I'll show in a moment. So there's other big caveat with threads. So you often hear multi-threading in applications that you run maybe on your computer, and it's used often for a common use. For instance, if you're writing data or reading data, you might have a thread that's doing the reading and writing, and another thread that's running the GUI of your application, another one that's doing some computations, and that allows you to keep things like GUI processes, graphical processes, responsive. So you don't want it, so when you click a button on your GUI, the whole GUI freezes while it's writing a file or reading a file. You'd have a separate process for that, or a separate thread for that. So there's a few problems with this. So memory sharing is a big issue. So if you have multiple threads, and they're all sharing one bit of memory, and some of them are reading and some of them are writing from that memory, The big problem that you encounter is that the order in which the threads run is not defined, or you don't get to choose it. The operating system may run them in any order at any time. They might stop one for a while, the others three run longer. You don't know. That means that if you have two threads that are accessing the same bit of memory, what actually happens afterwards can become undefined as well. That means that the order in which they access that memory can change the results of what you expect, right? And this is something called a race condition. That this means that they're both two or more threads are racing to see who can access the memory first, and whoever wins gets it. But then the result is what they write to the memory, not what the next thread writes to the memory. So you have to always keep this in mind, that when you do multi-threading and you're trying to share data, it's not simple. It's really not a trivial thing to write multi-threaded code. And generally you should avoid it, to be honest. But there's ways around that to make it easier. So the way that it's usually avoided is by locking memory. So there's methods in programming for how to tell all the threads that, hey, I own this memory right now. You aren't allowed to touch it. Only I can operating on it. When I'm done, I'll unlock it, and then you can use it when you want to. But even with that, it's very easy to make mistakes. So you can get deadlocks, which is where the code or two threads they acquire the lock maybe, but don't release it in the right order, and such that one's waiting for the other, and waiting for the other infinitely, and so your code just hangs. That's one of the common causes of hangs on modern computers that use a lot of multi-threading. So one of the methods that I would always suggest, and I think it's generally in all the code that we're going to show after this, is to use the fork and join style of parallelism. And that means that I have some problem. I want to divide that problem into pieces. So I divide the problem into pieces. I assign a piece to each thread or each processor, whatever you want. When those are done, we somehow wait for all of them to finish. We then use a process that's not parallel to bring the data back together, put it back together into the right pieces, and then continue on. So this way you avoid each let's say parallel piece of processing here, each thread is never needing to share memory or overwrite what the other thread is doing. And this avoids the problem of unintended collisions between threads. So this is actually from Wikipedia. I printed this as a nice little pseudocode for that. So you want to solve the problem. This is not real Python, of course. So if problem is small enough, just solve the problem directly. Normal sequential algorithm like you normally would. Otherwise, for each part in the subdivision of that problem, fork a subtask or create a thread in this case to solve that part. Then join all those tasks in the previous loop, and then return the combined results. So combine them together and put it out. The good thing is Python makes this very easy to do. But before we talk about how to do it, I wanted to make something about, another caveat about how Python does multi-threading and multi-threading in general. So Python actually is very, very bad at multi-threading. So if you've ever learned Java or now modern C, threads are really recommended all the time. And threads are very fast and they're great, and they often can help speed up a program. But in Python, there's something called the global interpreter lock. So this is a memory lock, just like I described before, that locks shared memory when the interpreter is executing the statement. That's to prevent these type of collisions. And it's actually part of the design of how Python executes, at least how CPython executes. But that means that because all memory is locked between statements of the interpreter, that in practice, all Python threads run on the same core. It means that you can have multi-threading. So it really does look like code is executing in parallel, but because they're actually, if you looked under the hood, they're actually running in sequence, might be a kind of random sequence, but they're running in sequence. They always run on one core. So you're not actually getting the benefit of multiprocessing. So the benefit of multiprocessing is that you have multiple processes and each one runs on its own core of the computer, or they get divided up among all the cores that are available, and then for you use all the power of your computer. Python can't do that. However, it's still useful to do multi-threading in Python for things like waiting, blocking operations, waiting for some IO to come in. Having that in a separate thread will still speed up your code, but it won't really run multi-core. It's still always one core. Unlike in C or Java or something where multi-threading really will run on every core. Unless, depending on how you lock the memory internally yourself, you still have to manage that, but it's easier to get multi-core performance. So generally in Python, you should prefer multiple processes, even though they're slow to start up and you have a bit of overhead in memory, to threads, because those really do run an independent. They actually start up a new version of Python for each process, and you get an overhead of starting them up, but then you have no problem with this of using all of your cores. Now there's another caveat, which is that when Python runs compiled C code, or Fortran or Numba or whatever, Numba is important here, multiple threads can be used inside that code. So up until they return to the Python interpreter. So inside a block of code that's compiled, you can have multi-threading, and that's something we'll show next. So there's a couple things you can do. So first of all, like I said with the previous, you can do nothing basically if you want to get use multiple cores on your computer, and that is because Numpy and SciPy operations use these underlying libraries. I already described this a bit, like BLAS, the basic linear algebra subprograms, which were created in the 70s. And these things are not only heavily optimized, the current ones used in when you install this from Anaconda are heavily optimized versions that include automatic vectorization of codes. They automatically use the SIMD instructions of your CPU that I mentioned briefly earlier. And they also do multi-core parallelization automatically in some cases. So the two implementations that are usually used are OpenBLAS or Intel MKL. Both of these have a BLAS or BLAS implementations, and they both provide very fast speeds. It's particularly the MKL1 that you get with Anaconda. So if you use functions like mp.dot or whatever, or something from any of the linear algebra library or any of these standard NumPy functions, generally it will automatically run on all the cores of your system. If the problem is big enough, there's some, I think it does make some decisions about that underneath, because sometimes the overhead of starting, running multiple threads can be larger than just running sequentially. And actually that's something. So yeah, the point here is that you can benefit just by, again, just write NumPy code and avoid loops, write NumPy code, and you'll use very efficiently your CPU. However, this is actually something that you might want to turn off. And to do that, you actually have to export a few environment variables in your shell, like MKL num threads, num expression num threads, and OMP num threads. These are all, by the way, libraries. This is a C library that's used underneath in some of these implementations to do multi-threading. And the reason why you might want to turn off this is that sometimes if you're running code on a shared batch system, a shared machine, there's policies that say you're not allowed to use more than one core. In which case, we've run into this problem in our analysis for CTA and HES, for instance, where of course people write code in Python don't realize they're actually automatically using multiple cores, and so you have to actually disable it to be policy compliant. So it's something to think about. So basically, you can do nothing and still get some benefit. If you want to do something a bit more, have a bit more control, because you have no control over what those codes do underneath, you can do automatic parallelism with Numba. So remember that this global interpreter lock only affects Python code, not compiled code. So inside a Numba expression, we can use threads as normal. So Numba makes this really easy to do parallel loops without even having knowing how to do it. And this ngit operator that we're already using has an option you can pass to it called parallel equals true. And what it does is actually quite clever. It tries to parallelize everything that it can by enabling that. So it actually looks at your for loops and it tries to figure out if they're in the right order, by the way, so that sometimes it can matter whether you loop over the smaller element in an array first versus the larger element in the array. It depends on how the arrays are in memory, whether it can then turn those into vectorized operations that can use your SIMD parts of your CPU. It also depends on what it can actually send equivalent in a efficient way to different threads. So you can also tell it a bit specifically which parts should be parallelized using this p-range, basically replacing anywhere we use range with p-range, and that tells that particular block can be executed in parallel. So here's an example. So you just turn on parallel equals true. You have some function that has for I in p range 10, for j in range 1000, do something ijn. So that says, well, these can be done in parallel. So this whole inner step can be separated and run independently on threads. And I'm okay with that. You have to be very careful with this though. So then this part will not get parallelized in threads, probably, unless somehow when it does this optimization step, it says, oh, I can also parallel this. It'll do it for you automatically. So this allows you to divide a problem up tell where you can tell it where you should divide the problem up into sub pieces. Now, there's a problem here. So if you do this, for instance, like this, so this is an example, I think, from the Numba website. So here's NJ pair equals 2. I have n and y defined here as kind of shared memory here. And remember, now this is running parallel. So this statement, y, it's overwriting all of y with x of I plus equals x of I, runs in random order, right? So this, if this gets parallelized onto 3 machines, this gets executed 3 times in random order. So the result you're going to get is not going to be what you expect. So you have to really be careful about this. You can't just automatically put it and say, oh, this is parallelizable. It's not parallelizable because this is sharing memory, and the shared memory cannot be accessed all at once. So you're not guaranteed to get the right result here. Just a side thing to mention with C++, I mentioned this OpenMP. That's what's used in a lot of C code now to automatically parallelize. So you can always, it makes writing parallel code in C very similar to how you do it in Numba. So you put these like special statements, number, pragma, OMP, parallel 4, and then that's basically the same as doing P range in Numba. So that if you're running C code, you can do things like this. This also works in Fortran, I think, as well. Just for those people who aren't doing all Python. So let's do a demo of this, and let's see. Just switch back again to my find it. There we are. So here is that we're back here at this notebook that we ran before. Let's check the time here at 12. Yeah, perfect. So let's do the same thing. We'll take the solve. We already had the solve heat equation numpy numba. I'm going to take that one because that was this one here. It's not the fastest one, but it looked nice. I'm going to engine it with solve heat equation. Oh, sorry. No, I actually took the numpy one, not the. Oh no, that's right. Yeah. So I'm taking the numpy version. I want to numba it, but also put on the parallel equals true option and see what happens. One thing, so let's just plot it to make sure. Well, first of all, let's look here. What happens here? The function I get back, equation number. First of all, you see that it's a strange object. It's a CPU dispatcher function. So this is actually because it's going to run parts of this on different CPUs. And you can actually type. I always have to forget the option for this. Let me just. It's in my slides, but I don't want to go back to them right now. Parallel diagnostic. There's a function, so you can call on the function itself that got returned. It will tell you. It'll just die, I guess. Oh, because probably have to run the code first. That's right. So first I have to run it. Because the code has to be compiled first. So okay, so it gave the same result. I can run parallel diagnostics on it, and it'll tell me a bit. No, it's not going to want to do it. Okay, I don't know why. I'll go back. I have another example of this. Oh, because I'm calling the wrong one. Of course. Numpy number parallel. I don't type it properly. What am I typing wrong here? Numpy number parallel. Don't see a problem here, but let's just cut and paste this. Yeah, okay, I typed something wrong. What that will do, let me just move this over a bit, is actually show you what it was trying to parallelize inside the code. So it'll actually say, it actually says here that it looked into parallelizing these 2 loops. But actually it says the parallel structure is already optimal, so it didn't have to re-optimize anything. I think it did parallelize then these 2 loops, if I understand this correctly. So it tells you a bit about what it did. You can take a look and see what's actually happening. And you see the result, it worked. Let's run our time it function again on it. Let's move this back out again. Here's my cell that runs the. So now look up. So that's strange. So well, one thing. Okay, I didn't show you this. I should have opened up a. I can do this. Open activity monitor. On macOS, you can. Oops. So here's my. the other screen. Oh yeah, because I'm full screen. It will not let me do that. Let me make this not full screen. So here's all my processes, but I think I can turn on a view of my spew. Not up icon. I want to show you. I forget what this is. There's a way I can show you. Maybe it's this one, CPU usage. Yeah. So this, you can just see what the CPUs or what the processes or the cores are doing in my machine. If you run this, you at least see that. Let's see. Yeah, you see all of my cores are being used. They all went up. So it really is parallelizing onto multiple cores. That's a good thing. But you saw the results are actually not that good, and that's because this particular problem, the overhead of starting up multiple thread node is higher than just computing the problem. I think if I were to increase the size of the problem, so if I increased my initial grid to some very, very, very large grid, then you might see a benefit of this over the others. But by default, so this is why you have to think a bit about the problem, whether it's worth it or not. So yeah, there's the parallel diagnostics. Sorry, it's shown here. So version, and I put in into one of the for loops. Let's say this is actually the Numpy version, but I took the for loop over iterations and I put p range in there. We execute that. We run time it on it. I keep scrolling off of this every time. Rerun my performance. I think I have the wrong. I'm somewhere off my plotting script here. Sorry about that. Let's make this. That was my plotting. Okay, so you notice it went. Okay, great. First of all, I say great. Okay, it's much faster, right? So telling it that we could parallelize the internal that outer loop was really great. We got it much faster than Numba and Numpy, everything. But here's what I said. Okay, warning. That's why I have this warning here. Plot the result, and it looks a bit strange, right? So that's not the same result. If I plot it, let's plot two of these. How it was done by one of the algorithms and by the other algorithm, you notice it doesn't look the same. This after 10 iterations, it looks like a square and not like a fuzzy square, right? So, and the final result is not the same after 1,000 iterations. So why is that? Because I made a mistake here. I'm overwriting the current ZZ with the, this is an algorithm that takes the previous value, adds and computes a new one, puts the previous value on, computes the new one, puts the previous value on. So parallelizing that is bad because now I do these out of order, and now the order really did matter. This is time steps. So if I do the time steps out of order, I get the wrong answer. So I would have to think of a different way of optimizing this algorithm. And so this is why I say it's not totally automatic. You could think about how you might do this, and one way you might do it is divide the problem rather than passing like this updating each time step. Actually, it's not very easy. This is a problem that's not very easy to parallelize this way. I'll show one method later on, but you have to think about how you would divide it into a problem that can be use this for conjoined method. And here you can't really, because the previous time step depends on the next time step. So it's very different. This is not one you can easily parallelize in this way. So anyway, that was the caveat. So yeah, I got a better result, but I got the wrong result. So you have to be very careful there. So then the next thing I wanted to talk about there is, in the last few minutes, well, there's a few more things I want to show that I to show the parallel diagnostics. There's a couple other ways you can parallelize things not using Numba, just using pure Python standard library. And that's using two libraries, one called Concurrent Futures Thread Pool Executor, or processable executor. So this concurrent features module is part of Python 3, and it's a standard library that allows you to create either threads or processes, take a series of work and pass that work to those threads or processes, and then collect the results at the end. So it basically implements this fork and join in a way that you can't screw it up, basically, and it's very nice. But it doesn't give you the low-level control, as you will with the Numpy version. And so it looks like this. So you import concurrent features, you import processable executor or threadable executor. The nice thing is these have the same interface, so it doesn't matter. You can just, if you want to use processes, use this. If you want to use threads, use the other one. Remember that threads, however, will not run on every core. So this is not compiled code. This is not running code inside Numpy. So you really have to use processes here if you want to use all your cores. The other thing is you have to, I noticed somebody asked in the Slack, why do you have this if name equals main? Do you really need that, or to call a function? It's normally to block your code from executing if you import the code as a module, rather than, so it tells you this stuff shouldn't be run if it's imported as a module. If you're doing parallel code, this part is absolutely necessary. If you don't do this, it'll just crash and give you a cryptic error. So you absolutely have to put the code that runs inside main, or inside a function that's called inside main, or just purely inside a library function. You cannot, this will not work without this. And that's because when it runs this program, it actually runs this on every sub process that is being executed, and you don't want to re-execute this part for every sub process just for the first one. So it's a very strange copy. So anyway, this is how this works. You create a processable executor. Then for any piece of job you want to do, which is the work you want to do, you say, like, here's a function I define called work that just, again, it's the stupid one that sweeps 5 and returns x squared, but okay. You say pool.submit work, and then you give it a function, and then the values, let's say the arguments of the function, it can be multiple arguments if you want. Then you can, then that basically work is running on another process automatically. And here I just printed a little thing. I call feature.done a bunch of times every second, and you'll see what happens. It says it's done, no, and suddenly, okay, yeah, it's finished. So this is a way you can check if a job is done. But actually, if you call feature.result, that's a blocking call. It'll wait until the job is done and then return the result. So that's why it's called a future. This is a value that may be available sometime in the future. And the only time that you're guaranteed it's available is if you call result. And you can check if it's going to be, if it's there yet with done. So this is not the most useful example. This is a more standard example where you have, again, here's a work function. I made it a bit more complicated. I have it sleep for a random amount of time between 1 and 5 seconds. So it's slightly more different. And I have a bunch of values. So I want to compute x squared for all of these. Then I can do pool.map, and map works just like the Python map command. Gives it a function and an iterator of some kind, and it applies that function to every value iterator and returns a new iterator that has the results. So here's what happens when I run this. I get input, I print the input, I call pool.map, I actually print the output object immediately after. That immediately happens afterwards, and it just says, oh, it's an iterable, but actually there's no values in it. This is still lazy evaluation. This map is not yet been filled. And you see in the background, the jobs are computing the various elements of the array, but they're coming back in random order because, of course, I have a random sleep in here. So they take the time each one takes is random. But then when I turn the output back into a list, so this is a generator actually. So I don't remember if that was covered in previous talks. It gets very complicated, but Python generators are lazily evaluated. So you have to turn them into a list to explicitly show them as a list. And when you do that, the act of turning it into a list blocks and waits until all the values are there, and it puts them back into the proper order. So this is how you could execute this function in parallel on many machines or many cores. Let's see, 10 minutes left. So I'm going to probably cut a few of these things short. Okay, there's another option is to use an older part of the standard library called multiprocessing.pool. And it works basically the same, but a slightly different interface. And it doesn't have this quite the same way it does lazy evaluation. The interface is slightly simpler to use. Actually, I think it's easier bit to understand multiprocessing pool, but it comes from the old Python 2, but it's still part of the standard library. It also gives you more options to control how the jobs run. but it's not a standard interface. So the advantage of the concurrent features is that you can download other plugins that use concurrent features. I'll show you one in a moment, that allows you to use other parallelization systems, not just threads and processes to parallelize your data. So, but anyway, this one's also very easy, and I gave an example of these in the notebooks. The difference is basically is that this multiprocessing one that I just showed, the older one, like I said, it's a bit easier to understand, I think, but it also allows more control, like interprocess communication explicitly with pipes and queues, and provides this map-like interface. So does concurrent features, but the API is much, much simpler for concurrent features. That doesn't mean easier to understand. It's just less option. You have less control, but it allows you to do, maybe use more complicated systems later on. So it's more standardized. Both allow you to do not allow you to access shared memory directly. You have to use a mechanism to communicate with the processes, so it prevents you from making these memory mistakes, which is nice. So I would recommend playing with these, and I'll show you how to do those now. I think what I might not do is talk about multi-machine parallelism much, but I'll talk a little bit about it in the notebook. But let's see here. So let's open up the notebook on multiprocessing. I'm just going to close some of these little side things. I don't need them anymore. I'll close this. Okay. So remember okay, well, here's one example. Another real-world example is Monte Carlo integration, something that we do very often in science, right? When you have a big n-dimensional problem and you have an integral that you need to compute over that problem, and you don't have a good parameterization of the problem, you don't want to solve it analytically, you might want to integrate by basically throwing darts at the problem and finding out the difference in the number of darts that are in the area that you want to integrate versus the total number of darts you've thrown times the total area over which you threw all the darts. And that tells you the integral of the internal region. So I don't know why I printed hello here. I think it was just a test of my my thing was working. So here's one of the big caveats of doing anything with multiprocessing or or concurrent features or any of these. You cannot run them inside a notebook. So of course I'm going to run them inside a notebook here, but that's because I'm actually not running these in the notebook. I'm writing, this code is being written to a file called multiproc, and then I'm importing it again. It's just like when we did the optimization, the memory profiling. This will fail with crazy results if you run it in a notebook, because the way the notebooks work just don't allow parallelism. So what I did, okay, this is you can look at this on your own time, but this is just a function that calculates pi by throwing darts over a square area and then computing which ones fall that are within a radius of 1 from the center of that square area. And then it computes pi by basically finding that computes the area of a circle inside a square, and you divide the two, divided by the number of hits inside the circle by the number of hits total, and you get pi. So anyway, so I've done this in 2 ways here, and I showed Monte Carlo pi using multi-process pools, but also I think the one that you should look at here is using this process pool executor from so I actually call that one instead, from concurrent features. When I run it, what it's doing here is with process pool executor's pool, I basically take pool, I map my Monte Carlo pi function, which is this, which throws n darts. And what I want to do is repeat that call. So here I'm creating actually a list of inputs, but I used repeat. This is just from itertools. Repeat allows you to take a set of values and just make an array of them that repeats the same value many, many times. That allows me to call this n times. So I'm going to call it n jobs times with n total per job. So that's, you take 1,000 darts, and I'm going to run this. How many jobs did I say? I haven't executed it yet. So I can say how many jobs I want to do, 100,000 darts. Each one will give me an approximate result for the value of pi. And if I sum them all together, I get a much better result, of course, because then it's 100,000 times the number of jobs iterations. So okay, that's what I'm doing. So that's the entire process. So it's not running inside a notebook right now. I wrote this to a file. Now there's a file called multiproc.py that does all this. However, I can run the code once I've written it, all the functions that use parallelism to a file. I can run the code from inside my notebook. So I can import that file. And I can run parallel Monte Carlo pi and jobs equals 10 and total jobs equal 100,000, verbose equals true. So I'm doing 10 workers with 100,000 jobs each, and I get a value of pi that looks reasonable. Let's time it this and see what we got. So here I'm going to run. Now I've changed this to the total I'm going to run is 5 million, and I'm going to divide this always by the number of jobs I add. So I'm always going to throw a total of 5 million, but add more and more parallelism each time. So first time I run 5 million jobs on a single core, then I run 5 million over 2 jobs on 2 cores, and then 5 million over 5 on 5 cores, 10 up to 1,000. And sorry, this is not really cores, this is jobs. It automatically splits the jobs onto all available cores, and I have 12 cores on my machine with hyperthreading. So let's wait till that runs. It takes a little while probably. And you might notice that my CPU is using a lot of cores here now. You can see it at the top there. Okay, let's wait till this finishes. Okay, the first one finished already. I realized I probably should not run these all at the same time because, of course, the results are going to be a bit. They're all running simultaneously, so the results it take will be interfering with each other. So, okay, I should probably, if you run this by yourself, run one, wait till it finishes, run the next one, wait till it finishes. Otherwise, the results are not going to be perfect, but we'll see what we have. I may have to stop it after a certain point because this is. I maybe put too many. No, okay, it's running a reasonable time. You can see the time's going down already. I'm not sure. Yeah, I don't know if it properly accounts for multiple jobs running. Oh no, they should be running sequentially. So I think it's okay. No, it's okay. So forget what I just said. So you see it took 5 seconds for one job, 3 seconds for 2 jobs, 1.6, 1.4. So as we increase the number of jobs, we are actually improving the speed. Up to a point though, it's now gotten a little bit worse. Okay, probably should put less iterations. And now it's getting worse. And so what this is also telling you is that there's usually an optimal number of okay, this is also maybe just be timing error between them, but there's often an optimal number of jobs you want to start before you maximize the use of your, so just throwing 1 million jobs at something does not necessarily give you the best results. You want to find the optimal number of jobs for the problem that you're trying to solve. Okay, so that's basically done. Let's plot it. So I think I'm out of time. I have 2 things I wanted to cover, but I don't know if I should go over. We started a few minutes late, but I might just skip them. Yeah, so you can see that we got better up to about 100 or 10 jobs, and then we went above 10. It was actually not much better. So the number of jobs for the time you compute is not always it doesn't necessarily go linearly. You have to compute an optimization curve and see what the optimal number of jobs for your computer is. Depends on the computer, of course. Okay, so I think since we're out at the end of time now, the 2 things I didn't cover, but you can maybe look at on your own, or I can do a quick mention of them if you want, is multi-machine parallelism. This is actually a fairly complicated topic, so I think it's not necessarily worth going into too much detail here, just to say that it allows you to take jobs like to divide a problem into jobs, and each job runs on a different machine of a network that are on a shared network or on a shared cluster. With those, you have to sometimes exchange information between them. And I was going to do a demo of using the MPI library, but that's, I think, maybe a bit too much for right now. But I'll open it just to show you. For some reason, when my mouse seems to disappear for some reason. There it is. There's a example in here called MPI to IPI. And you can try this on your own. And this is another way of doing parallelism. And I'm just going to quickly mention this because I think it's important that MPI is a standard for doing parallel computing that's been around again since 1991. I think it's when it was created. And I used this back in many years ago, and it still works on modern machines as well as very old machines. and it allows you to run things either on multi-cores on a single computer or on multi-cores on any computers on a network. And so it's a very, very powerful system, but it requires a little bit of extra work and some thought because it doesn't do as many things for you as automatically. So I give you an example here. You can try running it. You actually have to run, again, you have to write it to a file, run it externally in a terminal. So try that on your own if you're interested in it. But I also want to point out that concurrent, the Python library I'm using for this, which is called MPI for Pi, provides a concurrent futures module that works just like the process pool executor called MPI pool executor. And so then you don't have to know anything about MPI. If you have an MPI cluster, a cluster that supports it, which many big data centers do, if you wrote your code to use concurrent futures, you can just run that code using MPI exec instead of running Python directly, and that code will run on every machine in your cluster at once. And that's really, really powerful. Okay, so I'm done there, and let's open up for questions.
Okay, thank you, Carl, very much. I'm taking over for the question. Axel had to run away. There was one not so naive question, actually. Since number.jit is efficient, do you recommend adding the JIT decorator to every function that has a loop and recursion?
That's a good question. I'd say no, because it's not totally always efficient, right? So it's only efficient for calls that are functions that are called very, very, very often, because there's always this overhead that the first time you call it, it has to compile itself. So if you put it on every function, actually the startup time of your program would just blow up. And it probably wouldn't give you any increase in time because of that. However, if there's a function you call 1 million times in your code, then yes, it's probably a good idea to look into using Numba. The only problem is that Numba is, has all these caveats. So you'll probably stick Numba on it. Use njit, not JIT, if you can. Otherwise, it really doesn't give you a performance increase. And you'll probably find that most functions will not just automatically parallelize or won't automatically compile. They'll give you an error. And it takes a lot of effort to write the function in a way that can be properly Numba compiled. But it's worth doing for functions that are very very often called. So what I look at the code that we've been developing, like Max and a few others myself, for CTA, and we have maybe 3 functions that we use, 3 or 4 functions that we use JIT in the entire maybe 12,000 line code base, and just those 3 functions increased the speed by an enormous factor, but we only needed 3 of them or something like it, something on the order of 3 or 4. So the amount of effort, it does take effort to use JIT. It doesn't just work totally automatically every time, but the results can be very important. But yeah, that's why I said, it doesn't really help you to put it on everything, but that's kind of what PyPy is trying to do, right? Is make everything in Python JIT compiled just like Numba. And the results right now is that for most scientific code, it doesn't speed it up.
Okay, thanks. And maybe a more specific question, which relates maybe to the MPI you showed at the end. How does concurrent.futures compare with joblib.parallel?
I don't know, actually. I haven't used joblib myself. I know it's used in scikit-learn a lot, and I think it's just a wrapper. Actually, I don't know. I don't actually know what does joblib parallelize onto multiple machines as well? I'm not sure if, or is it just a wrapper for?
No, it's a process pool as well, so you can on one machine run it on multiple processes.
Okay, so just
I think one of the major selling points of joblib was that it could more efficiently handle NumPy array sharing data between the processes, but that got a lot better with the latest pickle protocol that was introduced some time ago, I think in Python 3.8.
Yeah, so it might not matter. Joblib is around basically to maybe solve some problems that are not necessarily anymore, but yeah, it's another option.
So scikit-learn uses it still, so maybe there's still some benefits. I don't know. So if you're training scikit-learn models that allow parallelization, it will use this joblib module to do it.
My guess is if you look inside joblib, it's probably running a process pool executor or something like that underneath, something low level underneath. Maybe not. Maybe it has its own implementation, but I guess it just does better communication or something. But
okay, thanks, Max, for jumping in. Okay, last question. Is there a way to use PyPy has a default Python interpreter with Numpy, and then add another manually tuned parallelization level.
I don't think Numpy and PyPy work together, if I remember right. I've never tried it, but I don't think they yet work together. I might be wrong. Maybe someone can correct me, but they're really two kind of competing technologies. So basically, if you use PyPy, there's no real reason to use Numpy because it's already doing JIT compiling of everything. I don't know in PyPy if there's ways to give hints to tell it, how to compile things. That's maybe something I'd have to look into. I haven't used PyPy much. I tried it once you can install it, by the way, with Anaconda. You can install PyPy in an Anaconda environment, and it replaces Python with PyPy's version of Python. I mean, you can alias one to the other and see if it speeds up your code. For me, it actually slowed down my code quite a bit. so I gave up but the code I use heavily uses NumPy and things. So
yeah, so you have to try and...
You have to try it. It really depends on the problem. Yeah, I think some problems it probably really speeds up, right?
PyPy is great for optimizing pure Python code. So if you have, this is why these web frameworks, for example, make great benefits using it. But for the scientific code, it's almost always slower than CPython with the extensions on Numpy. So it's really something you can use for pure Python code, but for our use cases, it most often doesn't yield better results.
Yeah, that's why I would say it's a good project to watch, because I think maybe in the future some of these things will be solved and it'll be faster, but it's only faster in very specific situation where you write only Python code, which if you look in scientific code, it's almost never that we write pure Python code, right? We use NumPy, and just because even if you weren't trying to optimize things, NumPy and SciPy provide so many useful functions that aren't in the core Python library for math and science that you kind of have to use them.
Okay, well, I think we covered all the questions. Thank you very much again, Carl, for this session this morning. Very interesting and useful. So we end here the session, and we come back at 2 p.m. for GammaPy, and then Scikit app after. So thank you very much again, and see you later.